Okay, good afternoon, everyone. My name is Zhu Xu from Tsinghua University. I'm a PhD student, and today I will be presenting our work on modeling compressible reacting flows using deep neural network for tabulated chemical kinetics. So as we all know that simulating turbulent combustion is computationally expensive due to the wide range of chemical timescales involved. And the time required for CFD increases with the square number of chemical reactions. And this results in the fact that the integration of chemical kinetics can be 100 times more time consuming than non-reactive flows. So to address these challenges, various acceleration methods have been developed in recent years. So common acceleration methods in OpenFOAM are listed as follows. There are methods like adaptive chemistry, which reduces the number of variables locally, and some other storage and retrieval method like ISET. And thanks to DLB foam, it will be much easier for us to apply the load balancing and cell agglomeration method in OpenFOAM nowadays. And here we want to focus on using artificial neural networks for chemical kinetics tabulation, specifically through the DeepFlip framework. So actually, AN method for chemical kinetics tabulation is nothing new. In 1996, when my supervisor are pursuing his PhD degree, his fellows are actually doing the same thing as we do nowadays. Crystal, in 1996, first proposed an integrated PDF neural network approach for the simulation of turbulent flame, and he gets a 5 times speed up for the 2D hydrogen jet flames. So why the topic is hot again for recent years? Well, this paper by Dean in 2021 could explain why. In his paper, they sample not from the case they modeled, but from low-dimensional flamelet and random data. So they could develop a general AN method and applying the general mechanism to Sandia flame D and still get a benefit for time 12 times up speed up. And in 2023, John et al. Expand the idea by proposing using the cycle-GAN method and applied a Box-Cox transformation of multidimensional sampling of ODE calculation, leading to an AN model with accurate and robust predictions. So in this work, our motivation stems from the limited application of ANs in high-speed flow simulations. So in this study, we aim to simulate compressible reacting flows using deep learning neural networks and explore the acceleration ratios for different cases. And our ultimate goal is to pave the way for building a general AN mechanism for compressible reacting flows. But we haven't gone this so far, and today we are going to share some progress we made in recent days. So here is the overview of the cases we done for the recent days. There are 3 cases we're going to accelerate in this study. The first one is a 0D autoignition cases, which is an unsteady one. And the second case is a 1D reactive shock tube case. And the process of the case is shown in this animation, and I will talk about it later. And the last one is a 2D high-speed stepped wall combustor. The inlet Mach number is about 2.4. And before talking about the details of these cases, I want to elaborate the methodology for AN method. In this method, we apply a multi-layer perceptron method with 3 hidden layers, and the parameters are shown in the left column. And one thing need to be noticed is that we apply Box-Cox transformation with lambda value equals to 0.1 for input data pre-processing to address, to overcome the difficulty of training data with minor species. And of course, for the framework, by combine Cantera, PyTorch, and OpenFOAM together, we use the DeepFlame framework. So here is the data generation process for 0D autoignition. here we apply the hydrogen mechanism with 9 species and 19 reactions. We sample the data from 3,000 auto-ignite process, and the temperature ratios and equivalence ratios and pressure are shown in the list. And we sample about 4 million data points in this study, and the manifold are shown in this figure. And then we train the data. Takes about 24 hours using the RTX 3080 GPU, and both the training and validation data fit well with the ground truth values as shown in the right figure. So let's have a test about the AN computing result. Here it shows the 0D auto-ignition process is tested on different input combinations. The equivalence ratios ranges from 0.7, 1.0, and 2, and all of the results shows a good fit, and there is averagely a 108 times speed up, which is quite good. Okay. So for the next case we set up is a 1D reactive shock tube one, and the mechanism we apply is also hydrogen, and with 9 species and 19 reactions. And it's I have to talk about more about this case. This is a premixed tube, and there is a discontinuity in the middle. On the right side is the high pressure and high speed flow, and on the left side is the low pressure air. And so when you remove the discontinuity, you will see the gas propagates to the left, and when it hits on the wall, due to the stagnation process, the temperature and pressure will increase vastly, and you will see detonation process. And for the solvers, we apply a high-speed foam in deep flame. It has a KMP flux scheme. And for sampling strategy, we sample the whole process. And because the data points are too much, so we only sample the points with temperature over 1000 K, where detonation are likely to happen. And we sample about 20% of the data. And the sampling data is about 2.4 million. And here is the validation of the 1D reactive shock tube of the original CVODE solver. And as I mentioned before, we'll see the whole process. Here is where detonation happens. And on the right figure, we could show the modeling data of experiment, not experiment data, but from other more advanced method gets the data and fit also well. And so we train the data for the 1D reactive shock tube case, and takes about 12 hours to converge using an RTX 4090. This is another machine. So, and we can also see that both the training and validation data fit well with the ground truth values as shown in the right figure. So, yeah, here is the result for the AAN computing for 1D reactive tube. We could see, so here's the animation. Here's the ODE result and AN result. We could, well, I want to play it again. We could see that the calculation results show certain consistency with the ground truth results. However, as the number of iterations increases, the error accumulation leads to oscillation and the errors in the regions where the inference started earlier. So the more you iterate using AAM method, the more likely will cause errors and oscillations. No matter how the result is, we still get a 2.3 speed up comparing the CVODE result, 6 cores with the load balancing method. And if you do not apply load balancing for the CVODE one, you will get about 3 times speed up. And here I want to have a more word about the oscillation and error. I discussed with the panel of Deep Flame the other day, and they give me a lot of useful advices. And they tell me to look at the manifold of the sampling data. And the left figure is water and the hydrogen input scatter, because it's a narrow band. So once your inference data gets out of the manifold, it will be very likely to get wrong. So the right figure is the reaction rate scatter. We can see that for the reaction region, because the detonation process is quick and intense, so it results in very few data points being sampled in this region. So two possible ways to mend this is, the first one is data augmentation, such as we could use Gaussian sampling around this region, and it could be quite beneficial. Or we can sample more data with different initial conditions, and that could also be helpful. And we will do that in the future work. Anyway, so here is the last try we try on the 2D Boros-Kirchhoff combustor. So this is a high-speed stepped wall combustor. The inlet air is in the Mach number of 2.4, and the fuel inject velocity is 1 Mach number, and the time step we apply is 5 to the power of -8. And the sampling strategy is we wait until the computation comes to a steady state, and we sample for about 10 time steps of the steady flow field. And we only sample the region where the temperature is over 500 K, and the data points without hydrogen or H elements are excluded, because the reactions cannot happen there, because it's a non-premixed case. And the solvers we apply here is low Mach number foam with transonic pimple option. This is because we met some errors about high Mach number foam, and it turns out that there are some boundary conditions are not supplied, are not available in high-speed foam, and we will fix that in the near future, perhaps. And the sampling data is about 0.5 million, and the combustion model is PSR method. The turbulence model is K omega SSD with the wall Y plus number equals to 1, and the grid number is about 230K. So first, we have a validation of our solver for a 2D high-speed combustor. We can see that both a good agreement is achieved for the exit pressure and various outlet species distribution. Yeah. So we also train the data for the 2D high-speed combustor, and because the data set is quite small, we only sample for 10 snapshots of the data, and takes only 4 hours to converge using an RTX 4090, and we also get a very good result. So here is the test. We use AM computing for this 2D high-speed combustor. So the top figure is the steady state of the combustor, and now we're going to activate AM method to see what's gonna happen. So we could see that there's a slight change in this region, because we're going to see what's happening about the T contour. Okay, so we could see that the lift distance of the flame changes because there's actually a change in self-ignition time, which denotes the error of the AM method. But the overall result is quite good with the original CVOD method. And for the exit pressure and the species distribution, the overall trends are roughly the same. The overall distribution are roughly the same. But there are significant differences in certain local areas, such as water and oxygen, because the self-auto-ignition time is a little bit error here. Anyway, we still get a speed up as long as you adopt the AM method. So for the 6 cores with load balancing ODE result, there is a 4.7 times speed up for the case. And if you turn off the load balancing for CVOD, there will be a 5 times up speed up. So here is the conclusion. In conclusion, we have demonstrated the potential of applying deep neural network in accelerating the computation of compressible reacting flows. And in future work, we're going to we plan to add random data sampling to our database, and perhaps we're gonna apply our methods to LES cases and develop mechanism based on low-dimensional flamelets. Okay, thank you. That's all for my presentation.